Hello and welcome back to Dr. Neurosaurus. Today's Paleo Spotlight is Dr. Allison Bronson. Allison is a lecturer at California State Polytechnic University, Humboldt. She studies fossil sharks and fishes using CT scanning. We chatted about her path into paleontology, shark anatomy, and she answered the age-old question, what's the correct plural of fish? Let's dig in. Allison, welcome to the show.
Thank you. Nice to be here.
Nice to have you. What got you into paleontology?
It took me a while to come around to paleontology. So I'm friends with you. I'm friends with a lot of other paleontologists that say like, oh, I love dinosaurs from the time I was a little kid. And I did read some dinosaur books as a little kid. Like I had that Dinotopia book with all the beautiful illustrations, stuff like that. But I was never like a hardcore dinosaur kid. I loved fishes. So like I decided to be an ichthyologist when I was like 8. And so I was just on this track of like, I want to study fishes. And then I came to do my undergraduate degree where I now teach at Cal Poly Humboldt. And you could be in fisheries, but it was very like conservation and management focused. Or you could be in biology where there's nobody working on fish, but it was more biology, anatomy, evolution focused. So I went into the biology department and thought I was going to do like conservation and ecology of sharks, and then took an anatomy class and I learned about fossil fishes, and that like set me on this whole trajectory. So I ended up doing an internship actually on living sharks at the AMNH with the person who would then be my grad advisor on fossil sharks. So it was like a really long roundabout, like from reading some dinosaur books as a kid, suddenly like now I'm a professional paleontologist. Yeah.
It's actually really interesting to hear someone finally say, I've been interested in fishes for a long time, because
Yeah.
I've had a couple of interviews where people say, well, this thing is starting to look like a fish and we're not about that. That's not acceptable. Fish have too many bones.
I feel like I've gone maybe the easier route of fishes because sharks just have very not straightforward kind of, but like they have cartilaginous skeletons. Their cranium is like a little box with jaws stuck on it, not even that securely stuck on it. It's a much simpler skeleton. Like there are folks I know who work on like fossil lungfish, where there are so many bones in their head that they just like give them letters and numbers. I'm like, okay, that's not for me. Yeah,
Oh
much.
no. It's like when you do too much math and it all becomes letters instead of numbers.
We'll just start ranking these numerically. And I'm like, that's
it's not for me.
Yeah.
Can you tell us more about what you study specifically about sharks?
I'm really interested in the weirdest, oldest sharks. That's my favorite thing to work on is really, really old, weird sharks. And that's because sharks have been around for such a long period of time. They're well over 400 million years old. And so they've made it through all of these mass extinction events and all of these periods of diversification of other groups of fishes. And with each of these events, sharks get weirder and then contract a little bit and get weirder and contract a little bit. So when you look way back in the fossil record, contrary to what it's like now, or if you imagine a shark, there is lots of diversity out there, but you kind of like imagine a gray torpedo with fins and teeth. Sharks of the past had really, really crazy morphology. So I like looking at morphology where we're not always exactly sure what to expect. And it might not look like anything that we've seen before. So that's kind of my favorite stuff to work on. But I have a student right now who's working on armored fishes. So ostracoderms and placoderms. And I do recently now a lot more work on the anatomy of living fishes too. So both bony fishes and cartilaginous stuff. Mm-hmm.
So it seems like you cover a broad portion of the fish family tree between sharks and bony fishes and some placoderms in there and maybe lobefin fishes.
I try and avoid lobefin fishes.
Right.
They're complicated. Although that's actually, I also am working on a project on newts. So that's a lobefin fish, right?
It's true. Yep. Yeah, aren't we all?
It's humbling. Yeah, there are a lot of fishes. That's a stupid sentence. There's a lot of fishes. Just right now alive, there are over 36,000 species of fishes, right? But there are fewer people working on them than you'd expect. So we're friends with various mammalogists, ornithologists. There aren't that many mammals and birds. I mean, we got nothing on the beetle people or the nematode people, but like there's so much diversity in fish anatomy, and not a lot of people really excited to get into it. So it's like a surprisingly small, fun group of people that want to stare at dead fish and learn more about them. Yeah.
Okay, I have a really important question, something that needs to be settled.
Mm.
Is the plural of fish fish or fishes? And what's the difference?
I'm so glad you asked. So if you have a group of fish, they're all the same species. So like if you had a school of herring fish, or if you have one, obviously it's fish. But if you have a group of different species, it's fishes. Realistically, if you say a bunch of fish, no one's gonna come after you. But it's fishes.
What is your favorite fish?
There's so many really good ones. There's this fish up here. I have like different fish I like all the time, right? So there are two, one that I see relatively often here in Northern California. It's called the northern clingfish, Gobisox meandricus. They're like shaped like a teardrop with a giant suction cup on their tummy. And they suck onto rocks in tide pools. And they're just cute as heck. They're just amazing. They're really cute. If you pick one up, sometimes they'll like suck onto your hand, and they're just adorable. And they're like good, if you've got students like out tide pooling and they don't really know what they want to work on, if they meet a clingfish, it's like, all right, fishes are great. And then there's a wish list fish of mine out here that I've heard you can see living in these like big acorn barnacles. So like when acorn barnacles die, they leave kind of like a cone shaped, almost like a shell behind. And these fish like to live in there. And so whenever I'm diving here, I'm on the lookout. I've never seen one outside of an aquarium, but they're little and ridiculous looking, and they're called grunt sculpin.
Yeah. Ooh, sculpin. I know that word.
I realize I've picked two bony fishes, and I'm a shark person.
Yeah, no sharks.
There are too many good sharks. Like I'm teaching a class right now that's sharks and rays, and it's like every week in class I'm learning something new that I get to teach my students about some taxon within cartilaginous fishes. I didn't know they do that. I'm like, oh, I didn't know their structure is like this. It's great. So I can't pick a favorite shark. There's too many good ones.
I hear that.
Yeah.
Yep. What kinds of advice do you have for young aspiring paleontologists?
That's a good question. I think working on fossils means you have to be good at understanding anatomy and thinking about evolution. But anyone can be good at anything. Anyone can learn anything. So you have to convince yourself that you can do that. And then you have to convince yourself that you enjoy learning about that, even the hard parts. So two pieces of advice, I guess. One is pick a field or a part of paleontology where you enjoy even the boring parts, if that makes sense. Like a lot of what I do in the lab is like reconstructing CT scans or making slides, and those can be really tedious for some people, but I don't think they're so bad. So find a subfield of it where like even the stuff that might seem tedious, you kind of enjoy. Because there are no science jobs where it's just only fun all the time. And then the other part is that we increasingly seem to be living in a world where People associate a lot with image or a lot with rapid results. And paleontology is a place where most of your work is going to take a while. It can't come fast. It's going to be really difficult. You can't solve the problem very quickly most of the time. And it's also a field where, like, you're not going to be famous. You're not probably going to make millions of dollars off of paleontology. So you have to be in it because you really, really like it. And so if you can train yourself to pay attention to details and be good at reading the literature and like strong reading comprehension, that will serve you really well, because so much of paleontology is like reading a paper or book from 1920 and relating a drawing in that to what you're seeing in like an amazing high resolution CT scan that you made yesterday. So being able to bridge that like new and old requires a lot of reading skill and a lot of attention to detail. And those are things that anybody can build as skills, but you have to really work hard at it. Yeah.
Excellent. Excellent points of advice. I mean, that comment about in modern day, we're so used to quick results. We're so used to being able to like have a question and pick up our phones and answer our question.
Yeah.
And the scientists are not like that. Scientists in general just take a long time. And you know, paleo has taken millions of years. So
and the transition from being in a class and learning something or being able to look up an answer or check with a teacher or classmate, with students that I supervise, the transition to doing research and being the first person to ever find something out is really hard, because there is no right answer yet. Like, you're the person figuring out the answer, and that can be emotionally challenging for a lot of folks.
I've been working on a paper with a student where we were trying to, in CT scans, we were trying to figure out what a structure was in 2 dimensions in a species that had never been really figured.
Yep.
And so there's no source. We are constructing the source information for future scientists, and it's there's no way there's nowhere to look up the answer. You just have to keep struggling for a while.
Yeah, we're doing that right now, even with living species. We're working on inner ears, and there's like 12 descriptions of inner ears out there, and most of them are the membranous parts, not the skeletal parts. And so my students have to like just go along in the CT scan, and if they don't know what a structure is, it's like, okay, well, we're gonna render it, and then that's how we'll figure out what it is. Yeah, it's hard.
Here's a question for you. You mentioned rendering out parts of your shark scans, and that most of it is cartilage. How does cartilage look different than bone in both the fossil specimen and in CT?
Oh, good question. So shark skeletons are made of 2 different kinds of cartilage. So there's fibrous cartilage down there, vertebral column, and then the rest of it is tessellated calcified cartilage, which has these little tile-like structures covering the outside, and that's what gives it most of its like rigidity. And so the more mineralized that is, the better it fossilizes and the better it shows up in a CT scan. In the fossil record, ideally for cartilage, you'd have really anoxic, like reducing environments. So really acidic, really low oxygen, so that it inhibits bacteria from breaking down the cartilage before it can fossilize. So it's hard to find it in the fossil record. And then in CT scans, we have stuff that's been in collections for a long time. Usually that's okay. Sometimes cartilage gets weird when it's been in a collection for like 50 years. But if the skeleton is really mineralized, it shows up great. It's easy to segment. Most of the time, mineralization varies even from one part of the cranium to the other. So sometimes when my students and I are looking, for example, at these spaces of the ear, like there's cartilage that's more dense. Here's fluid, it's less dense. Sometimes it's like just a couple grayscale values different, and they're like, they have to trace everything by hand, because the computer can't tell where it begins and ends. You have to like look at the structure and figure it out. Yeah.
That's something that my students have struggled with too. Like, well, where's the automated tool that does this?
Oh,
I'm like,
oh
no,
no,
sir,
no.
you are the automated tool.
Yeah.
You are the tool.
You just have to
You,
stare at it.
you can see the differences in grayscale here that the
Yeah.
computer cannot because they're too similar. So that's what you're doing is going through each slice. And they're always like, each slice, it's like 1,200 slices.
Yeah.
Yep.
Uh-huh. Someday,
Yep,
someone's
cozy.
going to develop some magical segmentation tool, but we've tried a bunch that are set up for different kinds of materials. And because the density is so different from one end of even one skeletal element to another, it's rough. Yeah.
Yep.
Yeah.
Allison, thank you so much for being on the show today.
It's been great. It's always nice to see you.
Always nice to see you too. And we'll see you in the next episode.